So there will be no class tomorrow. I am not here. Actually, I was supposed to go today, but the meeting is tomorrow now in Chandigarh, so I am not here. अब वेंसडे को इस बार करना है, क्या करना है, आई डोंट नो. नहीं, बट आई डोंट नो हाउ कन्वीनियंट इट इज इफ वी. नहीं, आई नो दैट, बट इज इट कन्वीनियंट फॉर एवरीवन? आई डोंट नो. तुम्हारा क्या है? वेयर डू यू स्टे? मेरठ से आते हो रोज? एंड ओनली दिस. दूसरी क्लास कब होती है तुम्हारी? तो वेडनेसडे को होती है. लेट्स सी. सैटरडे को आई हैव टू सी. मैं बता दूंगा, फिर फ्राइडे को बता दूंगा. तो विल लेट यू नो ऑन फ्राइडे इफ इट इज हेल्ड ऑन सैटरडे. क्या हुआ, इतने कंफ्यूज क्यों लग रहे हो भाई? ट्यूसडे को नहीं है, फ्राइडे को होगी क्लास नेक्स्ट. उसमें डिसाइड कर लेंगे कि मेकअप सैटरडे को करना है या नेक्स्ट वेडनेसडे को करना है. ठीक है, तो बिकॉज जितनी जल्दी हो जाए तो ठीक है, क्योंकि देन ऑल्सो एनीवे वी आर नॉट सो फार लैग्ड बिहाइंड. इट्स 25th टुडे. आई थिंक 27 टोटल हुई. आई वांट टू टेक अबाउट 40 लेक्चर्स, सो आई थिंक आई हैव टाइम इवन इफ आई डोंट टेक द मेकअप क्लास. बट लेट्स जस्ट ट्राई टू. पर मेकअप लेनी है तो जितनी जल्दी हो जाए उतना अच्छा है, रादर देन टुवर्ड्स द एंड. दैट्स माय. ठीक है, ओके. सो नाउ today I think things may get a bit more interesting now. Well, anyway, what we are trying to see, I think most of the time what we have been doing in this course is trying to look at order of magnitude of various terms and try to get the physics from the equations. Okay, so now we'll start with chapter 4, which is turbulent shear flows. And in this chapter, we will look at boundary free flows, which means chapter 5 will deal with flow next to a boundary or a boundary layer, turbulent boundary layers. And what this entails, we'll just have a look at this. So now, when we talk of shear flows, shear, what's the meaning of shear? That if you physically, if you try to look, that there is a slipping of layers, or there is a cross sliding. That is what we mean by shear. So here in boundary free shear flows, what we are going to look at is that there will be one main flow direction. There will be a flow direction. In the flow direction, the flow changes, but we will look at mainly 2D in the mean sense flows, where evolution of the flow along the streamwise direction is slow. And I'll explain what this means. And mainly what we will look at will be plane flows, and axisymmetric flows. When we talk of plane flows, then we say that the mean velocity is confined to planes. So, mean flow in a plane parallel to the given plane is identical. Suppose we talk of a planar flow which is planar in the x1, x2 plane. That means whatever is the mean flow in this plane, if I look at a plane parallel to this, then the mean flow will be identical in the parallel plane, which is, so that means across the z direction, across the x3 directions, things will not change in the mean sense. Fluctuations could change, but in the mean sense, if I look at one plane, I get some sort of flow in the mean velocity distribution. When I change with x3, the mean quantities will not change with x3. They will only change with x1 and x2. And in most of these flows, you will find that there will be one direction of velocity which is sort of predominant, which we will take as the x1 direction. So, we will mean in the y direction will not be 0, but the predominant direction will be the x1 direction. That means the flow and structures are travelling downstream in the x1 direction. They will change with x2 also, they will evolve with x2, as we will see, but this is what we mean by a planar flow. x3 direction mein mean quantities will not change. Any averages, any statistical quantities will not change with x3. Maybe I will write it down explicitly. So, if x1, x2 is the plane, then statistical quantities do not change with x3, and mean of the z component of the velocity will also be 0. In axisymmetric flow, we talk of the r, theta, z coordinates. And what happens in axisymmetric flow? Things do not change with what direction? They will not change with theta, as far as there is a circular symmetry. So, if we look at r, theta, z, so in these flows, statistical quantities do not change with theta. And this will mean that mean flow planes, mean flow plane will be RZ plane through axis of symmetry will be identical. Okay. Now, what will be our methodology? First, I will describe the three type of flows we will look in this boundary free flows, and we will look at these flows for planar geometry. For axisymmetric, the results will be given, and maybe we can have a look at these in the assignments or something. How do we get to those results for axisymmetric? But we will have to follow essentially the same way as we followed for the planar methods. Okay. So, we start. So, we look at plane flows in detail. Yeah.
Can you explain this statement, mean flow planes through axis?
So that means if you have, so if you look at a plane through the axis of symmetry, and you look at the basically, this is R, this is Z. So you look at not this plane, RZ plane through axis of symmetry. So these planes, whether you are looking at theta is equal to 1, theta is equal to 2, theta is equal to 3, they will be identical, because things are not changing with theta. Okay. So now in the plane flows, we will look at mean velocity is in the x direction. This is the major component. Flow is in the xy plane. So mean of ui will be mean of u, mean of v and 0. The three components of the mean velocity will be x component, y component and 0. And d by dz of any statistical quantity will be 0, and we will impose the slow evolving condition, which implies that because we are going in the downstream direction, the derivatives with respect to the x direction will be much less than derivatives with respect to y, particularly of the quantities related to the velocity. No, this is, so in boundary layer also this will happen. So this is basically because of the shear flow we are talking of. That shear flow which is evolving, and let's physically look at first the flows which we are talking of, and then we will see whether this makes sense or not. ये fully developed technically नहीं, अगर fully developed होता तो d by dy 0 ही होता, और d by dx would have been 0 instead of much less. So the flow is evolving. जैसे बाउंड्री लेयर में भी होता है that things change with x. It is not in that sense fully developed, but it is something like fully developed. So it's like मतलब slowly developing, not fully. Fully developed होता तो d by dx would have been 0. No, we impose the slow evolving condition.
And how does this result into this?
Because see what's happening is that if the flow is majorly in this direction, then if it is evolving slowly, then the derivative changes along this direction will be much less than compared to what is happening in the cross direction. Okay, so it is something like what he said. It is like a fully developed flow, but not fully developed. Okay, so now the three type of flows we will talk of here. Firstly, we talk of a wake. Wake means that there is a body, and there is far away there is uniform flow with velocity u0i. Okay, there is only one component, and then if we look at the region here, this region, so there is fluid all everywhere. The region behind the body is what is termed as wake. And what we find is if we go downstream of the wake, or this is the middle line. So if I look at the velocity profile here, just behind the body at that plane, the velocity is less than the far away velocity u0, and as the sort of, if we look at the distance versus y, after some time, after some distance y, this velocity reaches u0.
Sir,
Yeah.
wake, definition of wake will depend on u naught, right? Because जितना ज़्यादा u naught होगा उतना बड़ा wake होगा ऐसा कुछ.
It will depend, उतना बड़ा होगा तो it will be scaled with u naught, will be one of the scaling things, and then bada means in this direction you are saying, of course.
In this also.
No, in this direction also, see, what happens is that what we talk of the wake, we talk of a distance which is about at least 10 to 20 distances down the body. And there we try to see what is the shape of this velocity profile. Does it take a self-similar form, or does it take a form which can be tackleable? Okay. So, this us and u0, these are of course, u0 is the mean velocity also, it is the instantaneous velocity also far away. We are assuming it is not turbulent. But in this region now, once there is turbulence, we will have turbulence here also. So, there will be turbulent fluctuations in the wake, and this us in this case is what we call as the velocity defect. The gap velocity, it is u0 here, it is us is this gap. So, the velocity at the center is actually u0 minus us at this center line. So, us is the defect compared to u0. ये S shear मान लो या कुछ, because this is what is causing the shear. Because we will use the same us for the other two flows also, so then it will become clear. So, this us is the basically velocity at the center line. Velocity, but here it is not the velocity at the center line, it is a defect. In the other two flows, we will talk of it as a velocity at the center line.
So, sir,
US.
velocity at center or
At the center, us is at the center. Now, we will also need, so this length, let us say, let us call this x dimension where we are measuring the wake, let this distance be capital L. Now, we need to define some sort of a y dimension also. Okay. Now, in this flow, because there is no channel or anything, there is nothing in the y direction. So, what we define is the height from the center where the velocity is us upon 2. So, in this case it will be, the defect will be us upon 2. We call that as small l. So, that gives us a representative height in the y direction, and because the flow is evolving, this L will change with x. Okay. So, the place where this defect is us upon 2. So, this height is what we call as small l.
तो फिर x के साथ us भी change होगा
और L भी change होगा.
small l
हाँ, what will you expect when x goes to infinity? What will be us? 0, because you will get that. So, us will also change with x, L will also change with x, and that is the sort of what we call, can we find a scaling with respect to y? Does it go like y by root x, and that gives us for all x, y some sort of a scaling relation? That is what we will try to develop from the equations. So, here this is just defining or telling what is us, what is L, what is capital L, and so small l is a typical y distance, which again we do not know. Capital L is the distance in x, in some sense it is known, that is the distance at which we are measuring the velocity profile, and this L is definitely much larger than small l. We are trying to work this out. u0, us we have worked out. So, these are the typical things in a wake.
so l is much larger than small l ये तो assumption हुआ.
ये, yeah, right now it is an assumption, but that follows basically because what will happen is that these sort of self-similar profiles will happen only very much downstream. So what we are saying is, yeah, you could say that this is an assumption right now, whether it can be, or maybe it is an what you observe.
So एक river flow में जब वो पत्थर होता है बीच में,
हाँ
तो same situation रहता है.
हाँ
So उस पत्थर के immediately just बाद ही तो वो सारा जो भी
हाँ, तो वो सारा यहाँ बनना शुरू होता है. बट देन इफ यू गो स्लाइटली डाउनस्ट्रीम, और ज़्यादा नीचे जाओगे उस पत्थर के पीछे, तो वॉट यू विल ऑब्जर्व इज सम डिस्टेंस अवे दिस बिकम्स u0, सेम वेलोसिटी. और ये जो एवरेज प्रोफाइल जो आती है, दैट टेक्स अ शेप लाइक दिस, the velocity. So if there's a stone here, you measure the profile here, then you will find that the biggest defect comes at the center, just behind the stone. And as you go downstream, this basically will merge into uniform velocity.
तो हम उस जो उसके जस्ट पीछे जो रीजन होता है जिसमें मैक्सिमम प्रेशर डेफिसिट बनेगा,
हाँ
तो उस रीजन की बात नहीं करते.
नहीं, we are away from that. So we are not just at that stream, we are away from that. We are not just behind the body.
सर इसका क्या जस्ट बिहाइंड द बॉडी रहे या ज़्यादा दूर रहे,
हैं?
मतलब जस्ट बिहाइंड द बॉडी रहे या फिर ज़्यादा दूर रहे, इसका क्या?
नहीं, just behind the body, तो what will happen is कि you'll have probably more stagnant type of zone. मतलब stagnant type या उसमें recirculation zone होगा, उस तरह का होगा.
ये एल ऐसे चूज कैसे करते हैं, क्या वैल्यू देनी है?
ये L मतलब this is again asymptotically it is a large value. That is how we
लार्ज
take it.
वैल्यू तो हमें क्या पता क्या लार्ज वैल्यू है?
हाँ, नहीं तो basically then this will go by the size, this dimension of the body. अगर ये dimension D है, तो L will be like 20D or 30D or something like that.
सर if we increase the length of that L,
हाँ
then it will
हाँ, तो then it will just become u0, तब तो इसका इफेक्ट खत्म हो जाएगा. So if capital L goes to infinity, you will essentially get this us will become tend to 0, and you will get a uniform profile again. Okay, so this is the first type of flow which we call as the wake flow.
ऐसा कह सकते हैं ये वाली जो प्रोफाइल है, मतलब कुछ रेंज है जिसमें प्रोफाइल
हाँ हाँ, मतलब ये क्या होगा, प्रोफाइल चेंज होगी, बट इट विल चेंज विद बोथ y एंड x, एंड दे विल बी रिलेटेड टू ईच अदर. क्योंकि वो दैट इज वॉट वील ट्राई टू फाइंड आउट द रिलेशन बिटवीन y एंड x, सो दैट कैन वी फाइंड इट एज अ फंक्शन ऑफ अ सिंगल वेरिएबल इंस्टेड ऑफ y अलोन एंड x अलोन. हाँ, सेल्फ सिमिलर, जैसे बाउंड्री लेयर में y बाई रूट एक्स आ जाता है लेमिनार बाउंड्री लेयर में. so that is what we will try to see if we can get some sort of a scaling like that. That is what we are trying to do. Then the second type of flow we talk of are what are called as a jet flow so in the jet flow what we have is that there is fluid coming out and it is mixing with the surrounding fluid. Now the two fluids can be the same or they can be different. It could be a jet of air which is coming and mixing in quiescent air, or it could be, let's say, a jet of water coming out in air. So, but then here what we are assuming is that the surrounding fluid is at rest. Now, of course, because of the movement of this fluid, the surrounding fluid may start to move, but far away from the body, this is at rest. So, this jet is being released in what we call quiescent atmosphere. So, and the jet could be of the same fluid or of a different fluid. So, here what you find is that typically, if once again I look at this distance L, then the velocity, the mean velocity profile of the jet, it takes a shape like this. This is what we call, and this velocity, the mean velocity at the center, is what we call as u sub s. We are using us now in a generic way, so this is the velocity at this point is termed as us. And once again, at this L, the distance at which this velocity becomes us by 2, we call that as small l. We could have called the total thing also as small l. We could have taken the point where it becomes equal to 0 and call that as L, that also would have worked. But we have taken, here we are taking it as where it becomes half of it. Okay. So this we are calling as small l. So this is what we call as a jet. And the third flow is what we call as a mixing layer or a shear layer. And here what we have is, there is a plate, on the top part we have flow coming in with us. We are neglecting the small boundary layer here, but basically here on the top part the velocity is us. In the bottom part the velocity is 0. So we are dividing this whole region into two parts. Y greater than 0, the velocity is us on the top of the plate. At the bottom of the plate it is 0. So this is at the start. So this is basically x is equal to 0. Now what happens after this? The two flows start to mix. Okay. So now this is what becomes, this is the location x is equal to 0. And so now after some time what you have is, you get a profile. So you get a mean velocity profile in the x direction, which is like this, and this is what we call as the mixing layer, where the top and the bottom have mixed. Now of course what could have happened is, in the bottom part you could have had us1 and us2, two different velocities. Then what would have happened? You would have got a mixing of those two layers. In fact, you could also have had a us2 which was equal to minus of us1. So then you would have exactly an opposite part. But then by a change of reference frame, you can choose it in such a way that the bottom velocity becomes 0. So if it is minus us, then you add plus us, so then the top velocity will become 2 times us. Just this is a change of reference frame. Okay. So because these are constant velocities, so you can change the reference frames without any change in the equations. So this is how a mixing layer is defined, and once again here the length at which you have us upon 2 is what we call as the length L. So these are the three type of flows, and we are looking at the flow much after the boundary. In the jet also we are looking at the jet sufficiently away from the origin. In mixing layer also we are looking at the flow, and so here now I could place this distance is capital L. And that is why these three flows are termed as boundary free shear flows. There is a shear which is causing the flow. Shear means a bulk velocity in the u direction which is imposed on the flow. that is causing the flow, and we are now, we'll try to study the turbulence or the this thing of these flows. Yeah. No, I'm just saying that the mean velocity profile in all the cases, what I have shown the velocity profile was of the mean velocity. So I should have written that here also. This basically is the, because there is a if it's a turbulent flow, there are fluctuations also. So mean of u looks like this. There's a profile like this. So again, these are qualitative this thing, and then we have to try, what we are trying to do is trying to look at the turbulent flow equations of these type of flows, these three type of flows. They are boundary free. क्योंकि no, boundary free because we are sufficiently downstream of this boundary, na. So that's why. So जैसे this is as compared to, suppose if I was seeing the turbulent flow just on this plate, that would not be boundary free, and we will do that in chapter 5. इसकी पता नहीं क्या है, मतलब मुझे पता नहीं है, US/2 भी हो सकती है, कुछ भी हो सकती है, मतलब इट्स नॉट एग्जैक्टली US/2 होती नहीं है वैसे. So
how would we even define center line in this case?
no, center line means basically at this location, wherever the plate was. हैं? नहीं, जीरो तो सबसे नीचे ही होगी ना, इन्फिनिटी पे ही होगी, क्योंकि ये दोनों मिक्स हो रही है ना. यहाँ पे इसका इफेक्ट कुछ नीचे भी आएगा. इनफैक्ट दिस एल ये US/2 ऊपर होगी कि नीचे, आई डोंट इवन नो दिस. इनफैक्ट लमलीज बुक शोज दिस डाउन, but I think it's probably more physical to show it up than to show it down. So, or maybe it is somewhere here. So, wherever you get that US/2, you call that as
Down compared to this separation.
through the plate.
Compared to.
So that's what. So I don't know where actually it is, but to me it makes more sense to show it up, that US/2. But wherever US/2 is, but hopefully it is not at zero, because then L will not be definable. Okay. So now what we find is that there are two velocity scales. We are going to look at the equations first in a general way. So there are two velocity scales in wake and one velocity scale in shear layer oblique jet. In wake, we have a velocity u0 for mean flow in the x direction and a velocity scale us for cross stream variation of mean velocity in the x direction. The x component of mean velocity changes with y, and that variation is given by this velocity scale us. u0 was the main bulk velocity in the wake, whereas in the jet and the shear layer there is only one velocity us. There is no u0 in bulk velocity there. So we can look at us can be looked at as the maximum of magnitude of u0 minus mean of u. Mean velocity जहाँ भी है, wherever whatever is this maximum of this deficit or the difference, that is can be looked at as us in the wakes. And also what we find is in the wake, far from the body, us is much less than u0. In jets and shear layers, u0 is equal to 0. The velocity at infinity for jet, and for shear layer the velocity at minus infinity, this is 0 and us is the total velocity. Okay. So now what one can do is one can write mean of u is equal to u0 plus mean of u minus u0. I am just basically adding and subtracting. So mean of u can be written as of the order of u0 plus us, and this will be of the order of u0 in wakes. In jets and shear layers, mean of u is of the order of us. I'll just make it very clear again. I've written it twice, but in wake, the mean of u is of the order of u0. But wherever its variation with respect to y comes, then you have to use us. Because the variation of u0 with respect to y is measured in terms of us. But in jets and shear layers, the mean of u is of the order of us itself, there is no u0. So now what we can do is we can use mean of u is of the order of, we use u hat, where u hat is equal to us for jets and shear layers, and this is equal to u0 for wakes. Yeah. क्योंकि biggest it is 0 at the top and it is us at the center. Let's look at jet. So order of magnitude will be us, and that is how the variation with y is also going with the same order. ठीक है. And similarly in shear layer में भी capital US है, फिर 0 हो जाता है नीचे, so it is of the order of US only. There is no u0 there. If we talk of the order of magnitude of the mean velocity in the x direction, there is only us. But in wakes, there are two velocities. So wherever u has to come, it is u0. But when you have to talk of the variation, then it is u0 minus us. So it is changing with respect to that with us. Okay. हाँ वेक में हम इसको u0, लेट्स डू इट, विल डू द एनालिसिस नाउ तो इट विल बिकम क्लियर. अगेन वहां पे भी चक्कर आएगा. देयर इज अ टर्म u du by dx and u du by dy. तो first u is just a u, so there we will use u0, and when you talk of a variation, then we have to use us. So let's proceed. Okay. So now we have defined, I didn't write it, but let me write this also, defined cross stream scale L as distance from center where mean of u minus u0 is equal to us by 2. Of course, you can think of mean of u is equal to us by 2, but for the wakes, it will become mean of u minus u0. Okay. This is capital U, we are talking of this. Now, given this, that's what I was saying, that du by dy will be of the order of us upon L, and du by dx will be of the order of us upon capital L for all the three flows. We'll also need a velocity scale for turbulent velocities, and we will use, as we have been doing in this course, u prime RMS. Lumley's book calls it small u, but we have been calling it as small u prime RMS. He uses u with a script, but writing that would make it confusing. So that's why, as we have been following so far, we will call it u prime RMS. And then I'm just writing it in the equations. We will get, this will be of the order of u prime RMS square. We will get minus v prime square or plus v prime square, u prime square. All of these will be of the order of u RMS. Now, what is u prime RMS relative to US? This we have so far not defined. How much is the turbulent fluctuation vis-a-vis US, which is the mean velocity defect or the mean velocity in some sense in the other cases. This we have not specified so far. All we have said is turbulent quantities are of the order of u prime RMS. And this we will leave it to our analysis, or we will assume something over there, and that will come in a bit later. Okay. Now, scale of mean u, we have said this is equal to, I call it u hat, which is either u0 or us, unless we get a derivative. Okay. So, this is the scale of mean of u. How do we get the scale of mean y velocity? This is mean x velocity. So, maybe mean of u is, how do we get this? And for this scale, what we will do is, we will go to the continuity equation, which we do in a normal course also. So, to get this scale, we go to the continuity equation. And the continuity equation tells us du by dx because this is derivative, so we will use us upon L will be of the order of v divided by small l.
So जैसे हमने x में किया
हाँ
वो डेरिवेटिव है तो वो US by L होगा
हाँ
तो ऐसे ही y में भी तो हो सकता है हम उसको ऑर्डर V में देंगे
नहीं तो उसको y में सी, इन y there is no particular velocity which is coming in from the boundary condition. See, here basically it was US, only thing it happened was in the terms of for jet, for a wake, that there was a U0 which came in the boundary condition. But when we talk of its variation, then in the variation only US comes in. So that's why now in V there is only variation. So basically you can think of V0 as 0. Even for a wake, there is no V0. So that's why this is just basically like what you are saying, US only. So what this analysis is telling you is the mean velocity in the y direction is, if you are sufficiently downstream, is of the order of US times small l upon capital L. And if small l is small, then the velocity in the y direction is not very large. So it is getting smeared, but this velocity is much larger, and that is what you call as an evolving flow, where bulk velocity is in the x direction, the y direction velocity is there. It cannot be neglected, but its order will be L by L times L, small l by capital L times US. That is the variation in the y direction will be of that order. Okay. So having seen this, now what one does is, now we will look at in the limit L by L tends to 0. That means we are sufficiently downstream. We are in the limit here. So now we will try to analyze the equations, and what we do is the continuity equation we have already used. Now in the mean velocity we have two equations, mean x and mean y. Now if you recall, at least when we do the exact solutions, we first go to the equation where things are simpler, which is the y direction. Because here we got it like this. In the exact solutions what you get is Vy is 0. So now similar to that exercise, we first go to the y equation. So we go to the y equation, and again we are looking at stationary flows, which means there is no. So equation for mean of V. Now the equation is Ui. If we look at this equation, it is mean of Uj this is the left hand side. If we divide everything by rho, it's mean of Uj dui by dxj, and we are looking at the equation when I is 2 and j has to be summed upon. So therefore this is mean of, put j is equal to 1, I get mean of u dui, I is still 2, so it is dv by dx1, so dx plus uj is equal to 2, so mean of v, ui is still 2, so dv by dx2, so dy. Now there is also a term plus there is d by dxj in turbulent flow. When we do the averaging, on the left hand side we also get d by dxj of ui prime uj prime. Let us see how we will expand this. So first put j is equal to 1. So and I still is 2. I is fixed at 2. So it becomes partial by partial x1, which is x, times v prime u prime. That's one term. Second term will be partial by partial x2 means partial by partial y of v prime. So v prime square. Okay. So let me write these two terms down. So this becomes equal to partial by partial x of u prime v prime plus partial by partial y of v prime square. This is equal to. So this is the left hand side. Is that clear? See, now we are using the equations. I think we have been doing too much. This is the first time I think we are going to the Navier-Stokes equation, applying them to a physical flow. At least otherwise we are just doing, we did some of that also in chapter 2 and 3, but we are mainly looking at orders of magnitude, which we will again look. But now on the right hand side, which are the terms? The first term we get is minus 1 over rho partial p by partial xj. Okay? So this will become, now j will be what? 2. So this second term will become minus 1 over rho. नहीं एक्स आई होगा, नहीं एक्स आई है, हाँ सॉरी आई, एंड आई इज 2, so that's why it is 2. And then we have plus the viscous term. Viscous term will just become nu, now it is divided by rho, so nu times d2v by dx square plus d2v by dy square. So then we will get plus nu times d2v by dx square. These terms don't change because they are linear terms. Only the non-linear term you get that Reynolds square term. So this is basically the equation for the y direction. Very similar to the equations, okay? But you have the extra Reynolds stress terms. Now what are we going to do? And I'll do that in the next class, but I'll just tell you what I'm going to do, and I'll do the same thing with the x equation. So next class I'll start with this equation, and we will look at order of magnitude of each of these, what, 3, 4, 7 terms. And then we will see what happens in the limit when Reynolds number is large, when L upon L, small l upon capital L goes to 0. And then there are, like, we'll not know the order of magnitude of some of the terms, like pressure term, we don't know what is its order of magnitude. So it will balance with the biggest term which is there, all other terms will be neglected. So by now at least we have become, should have become experts in trying to work out what are the order of magnitudes. I've already worked out what is V, what is U, their order of magnitudes. X, d by dx is 1 over L, d by dy is 1 over small l. V, we have already worked out the order of magnitudes. Similarly, when we go to here, u prime, v prime, we have already said it's u prime RMS whole square. D by dx means 1 over capital L. D by dy means 1 over small l. So we will work out the order of magnitude of all of these and then come to our conclusions. Yeah, sure. So that is my, so I'm going to do this for the y momentum equation, and in the next class also at the same time for the x momentum equation. Okay, sure. So this is what we are going to do on Friday, and maybe Saturday we'll continue with this, but hopefully this is more engaging than the previous this thing. So